So today, in the morning session, we'll have Erika Eiser from the University of Cambridge giving us an introduction to colloids, in particular, I guess, experimental methods and a little bit of history, I see. And looks like there's some demos also that have been prepared. So welcome, Erika.
Thank you. Shri, thanks for the very nice invitation to be here. First for the workshop and now for the school as well. And thanks to all the organizers and all his students and other people involved who made this happen. And it's really nice to be back to India. But today I first want to talk to you about, I want to give you a little introduction on colloids. And just to give you an idea of why colloids are so interesting as such is already the Romans knew about them, and throughout history people used colloids in various forms without knowing it perhaps, but colloids are really interesting. Okay, as Shri said, I'm at the University of Cambridge in the physics department, in particular in the biological and soft systems sector. Okay, now just to start, to give you a flavor of what the Romans already knew about colloids, look at this beautiful Lycurgus cup. This is glass, and when you look at it in reflection, it appears green, whereas when you put light inside, in transmission, it appears red. But it is almost pure glass. So usually we know that it's completely transparent. So where does the color come from? Now the secret, the Romans knew about that you had to do something about it, but they couldn't really figure out, couldn't control it, is to use colloidal gold. And some analysis made of maybe 10 or 20 years ago showed that indeed that there are some small silver and gold ions, colloids of about 50 nanometers in the glass. A very minute fraction, but it is sufficient to color the glass. So, I think this is just by accident, because at that time, Romans, of course, didn't make colloids as such. What you have is in a workshop, you grind down, you polish things, and little pieces fall off, basically. So you had mechanically machined it down to this size without knowing. So indeed, it was just on random addition of metal powder to glass to color it. Okay, but what are colloids? Now, we know that colloids by now are small objects, but are they similar to just simple liquids like argon or krypton, which have a typical size of about an average size of 1 angstrom, or less simple liquids like nitrogen, CO2, and so forth? They are all very small, and a priori you could consider them as colloids as well. Now there's another type of liquid on the other side of the size range, with a size larger than typically 1 millimeter. These are sand grains, pebbles, or bricks, which I call heavy liquids. Now, definitely we know that these heavy liquids behave fairly different to simple liquids. So the first person to coin the word colloid was actually Thomas Graham, a Scottish researcher in the 1860s, and he already recognized that there is something on a scale between nanometer and micrometer, and at that time they knew already the microscope, and they saw that small particles tend to stick together. And that's why he called them colloids. And colloids comes from, I think, from the Greek, meaning to stick. So, and moreover, they cannot be separated by filtration or gravity alone. Now, colloids can be coming in any type of shapes. You can have glass, silica beads, plastic, PMMA we heard of, but there are plenty others, Teflon particles, polystyrene, well, there are not so many different ones, but there are still other ones. It's hard to make them. And then you have clay particles that are natural colloids that you can break down. They are given by the two-dimensional crystal structure. They are typically very monodispersed in the thickness of 1 nanometer, and they are very polydispersed in the width, which can be about 30 nanometers for here on average for laponite. But you have also hectorite and bentonite and many other clays used in building or construction sites, and they can be up to a few hundred nanometers. But then you have a very different type of colloid, and these are viruses. Now, here a virus is a completely different shape. So a colloid is not a priori a spherical object. It can be any type of shape, as long as they are small enough.
So wasn't
yeah?
Did Faraday work on gold suspension?
So Faraday was actually the first person to recognize that the color associated with gold nanocolloids comes from their size. You can go to the British Museum or the Royal Society, and you still see Faraday's solution he made, suspension, because they are very light, although gold is very dense. They're still nice, stable suspension of gold colloids. Actually, just a small anecdote, in Paracelsus and in the Middle Ages, people knew how to make gold colloid solutions, and they are called gold red, and that was used as energizing drink at that time. So I'm not sure whether it worked, but the Red Bull of the Middle Ages, yes. So the question is now, is it only the size that between a nanometer and a micron that makes the distinction between small molecules and colloids? Is it only the size? But we do need still to make a distinction between these small molecules and colloids. And so the difference between colloids and these small molecules is just written down here. You don't need to know the exact structure composition of a colloid in order to understand colloidal behavior. Whereas if you want to understand, for instance, the phase behavior of water, you really need to know what the water molecule structure is. So that's very different. Colloids are truly different to simple liquids. So we don't care about the detailed atomic structure or molecular structure inside the colloid. We treat it as an entity with specific interactions. So the consequences are, for instance, as an example, is again this tobacco mosaic virus that, for instance, has a phase behavior that is completely determined by its colloidal character, whereas it has also a different function, for instance, a biological function that is not colloidal at all. So it has two types of functions. So you have to realize there are two things to a colloid. It's colloidal behavior, but occasionally you have also some other behavior in the system. And in that case, you really need to know the precise sequence of the matter. Okay. Now, the next step is how to quantify colloids, and we have heard a lot of work on simulations, on treating colloids. But the most simple way of understanding why colloids are the way they are is to look at the relevant energies involved, and they are only of the order of kT. So a nice example to see why a colloid is different, for instance, to a pebble, is taking the barometric height distribution, and that's just the pressure at a certain height above, say, ground, and it scales exponentially with this factor, Boltzmann factor, which is the potential energy over the thermal energy. Now, in order to make any meaningful measurements, you need to have a change in height of each single particle in the system that is of corresponding to, well, it's not quite this, that corresponds to kT. So that means, or it has to move sufficiently due to thermal motion. Now, we see, I indicated in this picture already that colloids are moving all around. Here, pebbles are very often sitting on the ground and don't diffuse around. So what, can we put some numbers to it? Can we put a limit to how big a particle needs to be quantified as a colloid? And for that, we just take h, an average height of that, is simply given by kT over mg. Now, m can be replaced by the difference, by a difference of densities between the colloids and the solvent in the system, so delta rho, and I assume the colloids to be here, for simplicity, to be spheres. And we say that h has to be of the order of r in order to do any significant or any reasonable measurements in the system. So putting this in, what you get is that 2r, or the diameter of the system, has to be about 1 micrometer on Earth. Okay. Now, when we do the same calculation for pebbles, we put in the numbers, and you see the distance it travels due to thermal motion, assuming a pebble of a weight of about 50 grams. It's 10 to minus 18 centimeters on Earth. So you would think, okay, this would be a very, very long time scale, and the Deborah number in that case must be gigantic, although people say, or it's written, that mountains do flow, but on very, very long time scales, certainly longer than a PhD thesis. Okay, so that's that, length scales. So clearly, pebbles cannot move, and they're not colloids. But how about we go take a ride in the space shuttle and say, okay, we take our pebbles along, say silence, pebble, crystallization, experiment in progress. And what we then would like to do is, okay, certainly gravity there should not matter, and I should see colloidal behavior in the system. But then, how long do I need to measure in order to see anything significant, to make a conclusion from your system? And for that, you just say that the typical, you know that the diffusion, diffusing its own distance squared should be about 2 times the diffusion experiment times the experimental time that you look at it. Now, at the same time, we know from the Stokes-Einstein relation that the diffusion coefficient is just kT over 6 pi, the viscosity of the solvent, surrounding solvent, times the radius of the diffusing particle. And therefore, we can compute a typical experimental time for colloids of 1 micron to be about 1 second. That's a reasonable time. You can do experiments, no problem. But you plug it in for 1 centimeter pebbles in water, you see it's 10 to 12 seconds to diffuse its own diameter. If you just keep it very in a closed box, very careful, and don't shake it, or, well, it doesn't matter whether you shake it, I guess. Anyway, you see, I don't want to send a poor student for years into the space shuttle and do experiments there. It will not be very, very exciting. Okay, so you have 2 criteria for distinguishing colloids from more macroscopic objects. It is length scale. It has to move on a reasonable length scale, also in a reasonable time, experimental time. You don't have infinite time to do that. And in order to repeat an experiment, you need enough time to verify it. So we can conclude that the physics of colloids is obviously different to pebbles, but it is also different to atoms. And in particular, it is different to atoms simply because of the interactions between them. Not that there are exotic new interactions between colloids that they may not exist between atoms, but the crucial difference is that atoms have a fixed interaction between themselves. You cannot tune the interactions between atoms. They are given by their atomic nature. Whereas colloids, you can have colloids and you can tune the interactions smoothly by changing your solvent, your surrounding, whatever. You can charge them up, you can treat them. And I give you in the next part of my talk a bit of an overview of the relevant interactions in the system. Now, yes?
How squishy are these colloids that you play around in the laboratory?
Now, you can play with it. Maybe when you think of the experiments by Pusey and van Meegen, you want to make sure that they are behaving more or less like hard spheres. Now, silica particles are fairly good. They are you can make them very hard, but the problem with silica particle, if you want to measure them on 1 micron large silica particles, they settle, they sediment quite quickly. And it's hard to density match because silica has a high density. That's why people use sometimes PMMA. Water would be preferable, but that's very hard. There are only very few ways of making Teflon particles with a refractive index of close to water, and you can not only density but also index match those. So in reality, they are not that soft. I mean, when you dry them out and you look under the scanning electron microscope or AFM, you will see that they are compressed in the end due to capillary forces when you dry them out. But not so silica spheres. Silica spheres stay fairly robust.
You can make them fairly soft, right?
Yes. So one thing that people play with is this NIPEM colloids, where they have a very beautiful property of when you change the temperature, they go from basically it goes from a collapse to an expanded state. In a collapsed state, they are fairly hard sphere. In the expanded state, I'm not quite sure. Wim, do you know? NIPEM?
What is the system charge of these things?
Yes. They're not used to, but they can behave soft. You can compress them and make them non-spherical in a way. But you can play with the volume of the thing by playing with the solvent quality, because the NIPEM is a polymer that is cross-linked, so you can swell it or you can shrink it depending on the temperature.
Does this experiment play White's group on microgels, which is poly-N-isopropyl acrylamide
NIPEM.
polyacrylic acid?
Yes. 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 You can change externally by using an external field. You can change their volume. So you can prepare them close to being dense and still liquid, but then you change the temperature, they expand, and then you have a densely packed system. So you can change the volume fraction in situ. And that's another problem that experimentalists have. To prepare hard spheres very dense homogeneously is not easy, because you want to have it homogeneously distributed and not drying or evaporating from one side and have dense crust and less dense interior. So there are very subtle differences. The preparation is can be very tricky for high volume fractions. Okay. Now, the interactions between colloids can be the most important. Yes?
Is it, can you just buy monodisperse?
No. Now, that's the other drawback of colloids, or difference to colloids, is between colloids and atoms. Atoms are monodisperse. So you know what you're dealing with. Whereas colloids, even when I buy them, even when we make them, they will never be 100% monodisperse. And that always brings errors in the experiments. Always. You will always have some distribution. And even when you pay a lot of money for a gram of silica colloids fluorescently labeled, is maybe a few hundred pounds, and it lasts you for maybe a month or two. In dilute solution, if you use them high concentration, they're much more. And you ask them to send to you 1 micrometer large colloids, but then you will see the odd colloid here and there that is maybe 5 or 10 micrometer in the system. You do have a distribution. The more narrow distribution is harder to see, but when you try to crystallize and you have polydispersity in size of more than 6% in 3D, you will never crystallize, and that's a problem. It is difficult. People try to fractionate them, but even then you remain with a polydispersity. Okay, that's why computer simulations are easier. You know what you put in. Okay, the interactions can be summarized into hardcore repulsion, the extension of the colloids, Coulomb interactions if you have charges in the system. Of course, the famous van der Waals interactions that are always there. And depletion, we heard briefly about depletion, attraction, and a very complex and rich system are steric stabilizations due to polymers. So you coat your colloids with some polymers. I will describe the first 4 more in detail, but in my second lecture, I will give you, towards the end, I will give you an example of that, but also how to measure the forces between them. So let me just briefly tell you what hard sphere repulsion really is. Again, you all know what it is. It's basically an excluded volume, but it is simply, if you have truly hard spheres, you have 0 interactions until they touch. And then the interactions between them become infinite. That's, of course, due to some Pauli and short-ranged Coulomb repulsion. And sometimes you can bring about this type of very hard sphere interactions with a steric stabilization layer with polymers, where the colloid is very large and the stabilization layer is very small. So then this is quasi-hard sphere. But important is you have no interaction between them and also no attraction. Now, charges are much more tricky and they're not straightforward, and actually the new book by Jacob Israelashvili, the new edition of his book on intermolecular and surface forces will come out, I think, soon. There's a whole chapter, big chapter of 30, 40 pages dedicated to computing these interactions as a function of salt concentrations, added salt. And what is important is that you have a charged surface with fixed charges, and away from that, if it is in equilibrium with a solvent, you have these charges are dissociated. You have counter-ions in solution, but you have, if you add salt, also co-ions in the system, and they fall off exponentially. Now, the way to describe this layer of counter-ions and co-ions close to a surface, to a charged surface, is best done by the electric double layer, which with a Debye screening length, a length to which this falls off exponentially, and this screening length is just proportional. These are just fixed factors depending on the charge that you use in the system. These are some constant prefactors with here the temperature, but what is important is here this density or concentration of your charged ions that you add to the system. So it will be proportional to the square root of the concentration of the salt that you add in the system. And this is all the same for 1,1 salts. So sodium chloride is just, the Q is just 1. But when you have other salts like magnesium chloride, and magnesium is divalent, it's a 2,1 salt, and you have 2,2 salts, and they all behave differently, but you can all classify the Debye screening length in that, and it will depend on the concentration, square root of the concentration, and linearly in the charge. Now, when you look at the potential, electrostatic potential of the system, within that layer, it falls off like this, and it can be simply described for a colloid-colloid pair interaction, the interaction between them, as some prefactor that depends on constants here, the Debye screening length, the size of your charges. But what is important, it is here something like a Yukawa potential behavior. You have a fall off of your potential, interaction potential between two charges as e to the power minus the screening length times the distance between the particles divided epsilon times r, the distance between them again. So epsilon is just a dielectric constant in the system. So what that means is they are purely repulsive and long-ranged and solvent-mediated, and then that shows you by playing with the added salt concentration, you can play with the width or the length of the or the range of your repulsive forces between the colloids, which you again cannot do with a fixed charge on sodium ion, for instance. Okay. So this is actually very important, and it's also very essential for the stability of cells, because if you wouldn't have charges in the system, they may all collapse or not be viable. But also it's responsible for a much more mundane situation, clays. When it had been raining here quite a lot recently, and when you walk over a field that contains a lot of clay, when it's wet, it's very slippery. And that goes back to the fact that clay particles are negatively charged on their large surface. When these particles come into contact with water, water goes in to dissolve the ions in there and to they will swell the clays, reducing the osmotic pressure by the released counter-ions in the system, and then they become just water layers that lubricate these clay particles, and that's why it becomes very slippery. On regular earth not containing too much clay, this doesn't happen as much. So clays become slippery just because of these Coulomb interactions and because of their platelet-like nature and that they are swelling. Not all clays, but there are quite a few swelling clays. Okay, so you can also do pottery. You use water to lubricate them. So that's all behind is Coulomb interactions. Okay, now van der Waals or dispersion forces, or sometimes London dispersion forces, are also there between colloids, and they are also not as easy to be computed as such for large objects. And I don't do a rigorous derivation of van der Waals forces, but I want to give you a bit of an idea what you can do with them and why they are important with colloids. Okay, now we know the typical dispersion forces or van der Waals forces between two atoms is scaling as is attractive minus some constant over the separation between them to the power 6. Okay, now obviously when we deal with colloids, we deal with billions of atoms in that one colloid. Now the question is, what is the van der Waals forces of a large object containing many atoms with another object containing equally many atoms? How to compute that, and do we retain this form? And is it the same whether I have spherical colloids or rods or plates or flat surfaces? Okay, so the change when I add one colloid to a solvent, then the change in dispersion interaction must be proportional to the density of my solvent times the polarizability of my solvent molecules times the difference, the volume that I have taken out of the solvent and replaced by the colloid. So I have here colloid density of my colloid times the polarizability, average polarizability of my colloid minus the one that I replaced the solvent with. Okay, now if I have now two colloids in solution, then the interactions simply between them, you see I have to replace this part as well. That means the interactions between two identical colloids must be just minus this density times colloid times polarizability of the colloids minus the solvent part, replaced solvent part squared. Now this square makes it, and is negative, makes it that it's always attractive in a solvent between identical particles. Now, we can also play a very cunning game here and say, okay, if I take two different types of colloids and I make it such that this term of the colloid, of colloid 1, is smaller than the term for the solvent, whereas this term here for the second colloid is larger than this, then I get here this term becomes negative and times negative, and you can introduce repulsive van der Waals forces. Yeah. Sorry, it's hard for me to hear.
It doesn't depend at all on the geometry of colloids, because when you compute van der Waals forces between two different surfaces,
No, it doesn't depend on the I mean, maybe it is slightly different if you take plate-like particles, but if you take two identical colloids, but with different polarizabilities and densities, and you see in a moment why, then you will introduce attractive van der Waals, repulsive van der Waals forces between these two different colloids. not between equal. Between equal, here, this is completely independent of shape at the moment, this analysis. The shape can be still implemented here, but this analysis simply takes care of your, in principle, it only takes care now of this factor here. The shape will change this scaling in a moment. Okay. Now here comes in what's so beautiful about experiments with colloids. Usually you cannot switch off van der Waals forces between atoms or molecules. They're always there, right? But you can switch them off between colloids. It's not that you switch them off just like that. You just make them cancel as such. But this is very important. So the special cases when you make this density of your colloids times the polarizability of the colloids equal to that of the solvent. In this case, you have no dispersion forces. Now, what does this mean in practical terms is simply, when you recall Clausius-Mossotti, it relates the refractive index of a system to the atomic polarizabilities of the system, of your material that you deal with. And in particular, you can write, I'm sorry, n squared minus 1. So little n is the refractive index, divided n squared plus 2, is just 4 pi over 3 rho times alpha. So this is our little term here. Putting that in here implies simply that in order to obtain no dispersion forces, the refractive indices between the system, between the colloids, the refractive index of the colloid and the solvent has to be the same. Now, if you work in a chemistry department or are close to a chemistry department, but even in the physics department, you will have that. Just for your own sake, to just know that it really works, take a glass cover slip for microscopy, put it in water in a little beaker, and you see still the glass very clearly, only that maybe the dimensions look now larger. Now do the same thing and put it in a beaker with toluene, you will have the impression that your glass slide disappears. And that's what's so beautiful. So when you switch off the van der Waals interactions, you also make your system transparent. If you have many particles in the system and they have very different refractive index to the solvent, it will appear opaque. Milk is opaque because you have casein micelles, and it's white because you have lots of droplets in there, and you have diffuse light scattering. Clouds are only water droplets. You will have multiple light scattering from all these droplets. But the moment you make, even at high concentration, the refractive index of the particles, scattering particles, and your background the same, it becomes transparent. And that's the way you can then look deep inside your sample and look at the structure away from confining walls and look at very nice little, at your structure really deep inside without any defect. Hopefully.
But if they're transparent, you can't actually see them clearly either, right? So
the trick is what you do is you just adjust your solvent. That's what people do, for instance, with what Pusey did with dynamic light scattering, and many other people, Dave Waits with the dense, when you look at a dense system, is you just adjust your refractive index of the solvent continuously such that there is only a little delta left. And you still can see scattering, but it's not multiple scattering, unless you want to see that. But you can also do you can also then do. You need a little contrast, and then you can also do.
But can you perfectly index match, but at the same time either make these particles sort of colored or fluorescent? Is that a way to
Yes.
deal with it?
So one thing that I think Alphonse did at one stage is you can make beautiful colloids where you say, okay, I make a fluorescent core and then a big shell around it, which is the rest of my colloid that is density matched, index matched with the solvent, and in a confocal you see then just these fluorescent cores, and you still can look deep inside. You can also do another system where you take from the same batch your colloids, you take away one part, you fluorescently label that, you mix it with your non-fluorescently labeled system, and then you only track these fluorescently labeled particles in your otherwise completely transparent system. So there are all sorts of ways of playing with that in order to access the structure inside. And now, but I will also show you in a moment later an example where the colloids become too small to be tracked, for instance, by confocal microscopy. So if they are only 2 nanometers or 20 nanometers or so, then you need different type of light, like X-ray.
So how close can you index match? Is it delta? What is delta?
I think you can do it fairly well. I've never done it myself so far, but you can. What people do is they have a mixture of two liquids. In particular, what I think the group Edinburgh group is doing, for PMMA, they have cis-decalin and another nasty liquid, and so you just by changing the volume fractions of the two liquids, you can slowly approach your refractive index, correct refractive index. It can be to 0.001, I think. So it's fairly small, the delta. So a change in refractive index. Just a question for the students here, before I take your question. Do you know what the refractive index of water is? Good. So what is the refractive index of polystyrene spheres? It's 1.56 for dense polystyrene beads. So for glass, for some of the silica, when you take regular glass, it can vary, and that makes it difficult to work with silicas. It can be 1.47, and toluene is 1.46, so you can get very close already. So you have a significant reduction. The numbers in refractive index are really changed, small. I mean, some of the highest refractive index materials are titanium with 4, but that's really hard to achieve. Okay, but this is important. The variations, the numbers are small. Your question.
Isn't this a statement about one particular frequency? Because epsilon is given that all of these quantities are frequency dependent. What happens in that?
That's true. If you have, but very often you work with fairly. It is true for polystyrene that it can vary quite a bit over the wavelength because you have over the visible range. So what you like to do is perhaps to do light scattering with a monochromatic light, and you adjust the right thing for that wavelength between the liquid and the colloids. That is true. You can have dispersion, but most liquids have actually fairly they are dielectric basically. That means they pass most wavelengths in the visible uniformly. but not all of them. That's true. There are differences. So you have to overcome that by using just one wavelength. Like, I love to use my little laser. This is my experimental laser before I do any real scattering experiments. I just hold my sample take my sample and I investigate it, and it's very scattering. Okay, doesn't look so good. But that's the way to first test your sample. You hold a laser pointer to your sample and you see what happens. And you take best two different ones, red and green. They can be different. Okay. Talking about refractive index, actually water becomes very opaque for X-rays of 1 angstroms. So then X-rays can be absorbed quite strongly. Water is just genius because it is only transparent within the visible light that we see, but it becomes fairly opaque to many other forms of radiation. Okay. Now, of course, now the really tough job is to obtain the dependence on the shape of the system. So we took care of the prefactor, the Hamaker constant called, which is this part that we looked at the moment. But what is very difficult is to compute the true van der Waals forces between two macroscopic objects. So what you have to do is you take a small volume element here, and then you take pairwise, people in general take pairwise interactions, van der Waals interactions, and then sum over all the interactions of all delta volumes of the sphere. Then you have to take the next one and integrate over all the others. And that's a tough calculation to do. Of course, there were people like, I think, was it Lifshitz or and London? Yeah, and many other people who did that calculations. It is only an approximation because it takes only two body interactions, pairwise interactions into account. It does not take higher order interactions into account. But for short distances, you obtain for two spheres a much more complex scaling of the van der Waals as a function of the separation between them. And you see it's no longer just a scaling law 1 over r to the power 6, but it can change depending on the shape of your particle. This is for two hard spheres at short range. For two flat surfaces, it becomes different, and for two cylinders, yeah, it becomes more complex depending on how they are arranged to each other. So the shape does matter here, and changes the scaling of this attraction, how it goes here to the very deep attractive minimum. Whereas I think in the long-ranged part, it goes back to the regular 1 over R6 behavior. Okay. Now, what is important is very often in many systems you come across a combination of the two, dispersion and screened Coulomb interactions, and they are called also Dealvo forces after Deryagin and Landau, both Russians, and independently in the late 40s. There was also a publication by Verwey and Overbeek in the Netherlands, and they came up with this overall scaling or overall interaction potential between two particles that are both charged and have van der Waals attraction. And now by playing with the added charge in the system, you can play with the overall interaction potential here. And you can, if you have adjusted the stabilization, the Coulomb repulsion well enough, you can create a small secondary dispersion minimum that is only of the depth of a few kT, with a barrier which is also several kT. Once you overcome that barrier, you go into a situation of irreversible aggregation. That's also called in industry sometimes flocculation, because then no matter what you do afterwards, you can't get them apart. Now, incidentally, a nice experiment, or not experiment, observation that you can make is when you look at a river that looks to you apparently clear, and but it always contains some, and it's sweet water, it always will contain some clay particles and also other particles that you don't see. When it hits the ocean, the salt water will screen the Coulomb repulsion, and you see that all of a sudden it becomes very murky. That's because of that. You play with that barrier height. If you add salt, the barrier height goes down, and you go from perhaps some secondary minimum where you can redisperse things to something that is irreversibly aggregated, and these big flocks give rise then to this murkiness because they will scatter light much more intensively.
Dispersion doesn't always win, right?
Sorry?
Dispersion doesn't always win.
Not always. If you do dialysis, so you take out as much of the salt from your system, dispersion will hardly play any role because it is then so strongly repulsive that you can get, for instance, crystallization of colloids, very charged colloids, in a very low salt or in a non-polar solvent. You can get crystallization at fairly low concentrations or volume fractions, well below the hard sphere limit. So you can get then, they are just rearranged such that they minimize the Coulomb repulsion between them. So you can get very large, low density crystals stabilized by repulsion. Okay, so this is what I just said. Now, depletion. Let me talk about depletion a little bit. And people have mentioned that before here in the workshop and, and perhaps in the last few days. The essence is that you have colloids, hard sphere colloids in the system, and you have free polymers. And it's important that the polymers are in a good solvent or in a situation that they do not want to adsorb to the colloids. That's important. So you can play with that, and when two colloids come as close as the size of the radius of gyration of a typical polymer in solution, then of course you start to deplete this zone because the polymer would lose entropy and it diffuses out. And then you have a net concentration of colloids outside that is larger than here inside, and that gives rise to osmotic to an osmotic pressure, which as such is repulsive, but the net effect is that you have attractive interactions. So you get very nice short-ranged attraction, and here the range of the attraction is purely given by the size of the polymer, the radius of gyration of the polymer, whereas the depth of the attraction is given by the concentration. The more concentrated, the deeper is your attractive well. And you can play then all sorts of nice games of playing how big these are, and they can change your phase diagram dramatically. Okay, so in summary, we showed that the colloids are like giant atoms, and we can control we can control their interactions and their size and their shape. So that's something that is easier. The only drawback is perhaps, yeah? The question was, what is the difference in interactions that you can play with? Now, I will talk in the second part I will tell you a bit about the surface force apparatus by Jacob Israelishvili. That's a way of directly measuring the interactions between colloids. Now, for charged spheres in electrolyte solution, you can play between hundreds of nanometers screening length, device screening length, where you start to feel weak repulsion, for very low salt concentrations. So you take out the salt concentrations, so it can be hundreds of nanometers, but you can screen it down to 1 nanometer if you add a lot of salt. So there, by adding salt, you continuously reduce the length, the width of your repulsion. The van der Waals is difficult, but you can just switch it off, say. Or what you can do is you can overcome van der Waals. Because van der Waals falls off fairly quickly, the way to overcome it is to coat your surface with a thin layer of polymers, and within that thickness of a monolayer of a polymer, the strength has been killed off, basically. And these can be between a few nanometers up to maybe a few nanometers, maybe 10 nanometers. If you take DNA, it can be very long, as you have seen. So you can, but you can't go to microns. I think that's tough. Okay. So having these interactions, you can start playing with the property start playing with the properties of colloids and get all sorts of beautiful phase diagrams and new materials, if you wish. So the next part is just the hard sphere system, and it has been talked of a lot, but just again, I like to remind people of why hard sphere systems crystallize and what their phase diagram is, just in order to then build on more complex phase diagrams. And so when you look at this, if you take a system, a closed system, it's important to think of a closed system of colloids, and they are disordered, and going from disorder to order, a little Maxwell demon would tell you, oh, that will cost me about 10 kilocalories. So when you go from disorder to order in a closed system at a given condition, that means the total energy should not have changed. And this is something that, so if I changed from disorder to order, I change my entropy. I also need to change something else in the system. And that is what I think Dan Frankel showed, is that when you have hard spheres freezing, then it is purely driven by entropy. That means, although we think this is the lower entropy region than this ordered system, then that's what we typically think. Then this is this is higher entropy than this one. That's what I wanted to say. Then this is not true, because we know that at high enough concentrations we have lower entropy in this disordered system than in this highly ordered system. And the reason is simply you maximize the volume for each particle to you maximize the volume it can rattle inside. by ordering. It's just simply an argument in this way that you can then achieve a higher entropy. So this is the preferred state at the appropriate volume fraction. So when we go, this is typically the phase diagram of a purely hard sphere system, and it is simply only one line. Temperature does not play any role here. And you start seeing freezing at 0.49 volume fraction of 49%. And here in this region you have coexistence of a liquid and a solid. Past here you start have the pure crystal here for hard spheres. It's always FCC, and then you go to even higher concentrations, and it goes into a glass, and you cannot reach the true close packing very often because this is simply an arrested state. Okay, so this was beautiful work by Pusey and van Meegen, and they realized that in experiments, and you have seen that picture now many times. Again, here you have an onset of crystallization in coexistence with a liquid. The fraction of the crystals is growing, and here you see it very nicely because it's simply the Bragg diffraction from the crystals and so forth. And then you start to form a glassy region. Here the crystalline phase disappears. Okay. So just to blow up to show how beautiful it is. You see the crystals here. For some reason the crystals here are much smaller. But okay. Now, just to give you an idea of, I showed that last week, an example of hard sphere crystallization in nature. We know these beautiful opals. The color is simply due to the fact that you have crystallized silica beads in the system. And these are called photonic materials. Now, photonic means simply you have a very good periodic arrangement of low refractive index and high refractive index, but it has to be on the length scale of visible light to see these colors here. But there are also photonic crystals at different wavelengths. You can build them for infrared absorption or for UV or reflection. But it's the problem why it is hard to build them is, again, coming back to the thing that you cannot make silica spheres on very large, or any spheres on very large scale, very monodisperse. That remains difficult. Experimentally, and it's just very difficult. Now I want to show you a system that is a bit different to hard spheres, and that's a system I was working on during my postdoc time back in France, and that are what I call almost hard spheres. And I will explain to you in a moment also why I mean almost hard spheres, because I can play with the hardness of it by playing with its component. What I mean is I work with tribal copolymers that are known as pluronics. The number here tells you only something about the ratio of the blocks and the total molecular weight. And here you have triblocks, 2 blocks of ethylene oxide that are water soluble between 0 and 100 degrees, and propylene oxide, which is soluble in water only at low temperatures, but not soluble in become non-soluble at higher temperatures. So I play with the solvent quality here, and that means when I increase the temperature from, say, 5 degrees to 12 degrees at a reasonable concentration, I start to form spherical micelles. And these micelles simply behave like colloids. That's another example of a colloidal behavior that is not necessarily a hard sphere, right? It can be something completely different. So we play with the water. Water becomes a bad solvent for PEO. Now, I show you not my best phase diagram because it's not completely correct, but what you get is, here's the concentration of the polymer in weight percent in water. Here's the temperature. If I'm at a very low concentration here, I didn't show it, then I even don't have micelles, but it is just simply completely, I still have 20 minutes, right? Yeah. Then it's still completely just monomers in solution. I start to heat up. I get here along this line the formation of micelles, and this is a micellar liquid. And then I forgot to draw in here a second line. Here's a very narrow region of micellar liquid coexisting with crystals, micellar crystals, and up here I have a completely perfect micellar crystal. Perfectly transparent, and these micelles are very small. They're only like 80 angstroms in diameter. So how to investigate something like that? You see that also that as I increase the temperature, the transition goes to lower concentrations. So only at this temperature, they would correspond to more or less a hard sphere system, corresponding to the volume fractions in the system. Okay. Now for this, I asked my assistant, they're sitting in the row behind Dave, and this is a poor man's way of showing diffraction. Can you make it completely dark? Completely dark. Dark. So if you don't move, I hope you can see it, but would when you look very carefully, yeah, when you look carefully here, you see that you see a diffraction pattern. And that's the diffraction pattern of a two-dimensional object. And that's something that you can do, everybody here can do. What you can do is you make lines on a piece of paper, you photograph it, you make a little film of that, you hold your laser pointer to it, and because you have a regular pattern, you immediately see what that's enough, Wim, thanks. You can do direct diffraction measurements. This is, you can do it on, no, you can switch on the light, yeah. So you can play afterwards with that. If you need a nicely woven fabric where you have lines going, let me see, I do this. Yeah, you have, huh? That's a good point. So if you take lines, then what you get in a diffraction pattern is perpendicular to the lines, equidistant spots. If you have, if you now add cross lines, like in your fabric, because you have lines woven things, you get spots, equidistant spots in this, and then you get basically other maxima here with higher order maxima and minima away from this side. And oh, it's not very nicely drawn. I usually, let me see. All right. So you should get a nice diffraction pattern if it's equidistant. So lines give you points. If you have a row of points, you scatter from a row of points, you get in the reciprocal room a set of lines perpendicular to the orientation of that points. And what is important, the distance, how they are spaced from each other, give you some idea about structure in the system. So you can play with that. You can take the lines and then you start to rotate the lines, and your set of points has to rotate as well. Now, this is important just to get an idea of what your pattern does. If you have a square pattern, and you can make a square pattern with dots or triangles or crosses, the structure will be the same that you get. And that's what we do with small angle X-ray scattering or any other scattering experiment. But I urge you to do that. It's real fun. So what we do is we went to the synchrotron in Grenoble, and because the scattering contrast in your system for X-rays are only electron densities, and you deal with carbon, oxygen, and hydrogen, and water only has oxygen and hydrogen, you need a high intensity to see any contrast. That's why, and you need also many of, and you need a low wavelength, say a lambda equals 1 angstrom. This is your sample. Now, what is also important that you can see is the larger your objects, scattering objects, the more narrow is your scattering angle. That means when I go to very small, when I go to larger objects, I have to increase this distance in order to resolve the scattering pattern away from the unscattered beam here. So that's why we use 4 meters in the system. You can also go to higher distances. I think at the synchrotron you can go to a separation of 8 to 10 meters, depending on the size you want to look at. Now, in this settings, we have a sampling range of 0.01 of Q vectors of 0.01 to 0.12 angstrom minus 1, which corresponds to a size of 50 to 600 angstroms. Okay, now the first thing that we did was look how big are our micelles, micellar liquids, and what you typically obtain is what we call a diffuse ring. It is very diffuse in the sense the higher orders are barely visible because it is also a very mobile system. But you do a static scattering and you average over all positions. From this liquid ring, we get an idea of how big the micelles are. This is at 15 degrees in the liquid system. Now we heat it up. And that's what you get. Obviously, we went from a totally liquid ring to a very nicely powder crystalline sample. And what you see, this graininess here, is you have formed many little crystals with different orientations. And as I said, if I rotate my sample, also my pattern rotates, scattered pattern rotates with it. So this is basically powder rings getting from my patterns. Now, I know what the structure is simply by computing the ratio of the Q vectors from 0, that's the center of the beam. This is just here a little thing, a beam stopper, because the direct beam that is not scattered is so strong it would burn my detector. So that, forget about that. It's just to screen the direct beam. And we look at Qi over Q0. So Q0 is the distance from here to here. And then Q1 would be this, Q3 this, and Q4 that. This sequence is specific to the type of crystal you have. And in this case, it is simply a BCC structure. Now you can play a lot with that type of thing, because we heard from Surajit yesterday about martensite. These are BCC crystals, only they are on a very different scale, And because the radius or the part of the structure, the building units are now 10 times or 50 times larger, I have a much lower strength of that. They are much softer. The larger the objects, the softer the larger the building units, the softer the elastic or lower the elastic modulus of your system is. So what we can do is we can shear it, and when we shear it sufficiently long, we get actually a single crystal over many centimeters of micelles. So I sheared it in situ online in my system. I stop and I measure, and I get these very nice diffraction peaks, and that means I have now only a single crystal in the system. Funny enough is my BCC patterns should only give me 2 diffraction spots, but I get 4 at the same distance, and you see that these 2 belong together and they are stronger, and that means simply I have 2 twins in the system. So I also see some symmetry. So I have twinning in my in the BCC crystal.
So,
Yep.
if I increase the shear rate further, does it melt them?
Yeah. So what you can do is you go hard, you shear harder. This is fairly hard shear. If I go to 300-second -1, I see all of a sudden the whole thing gets into what I showed you as a micellar liquid, diffuse ring. As long as I shear, because I can monitor the X-rays while shearing, the moment I stop, it's instantly a powder crystal again. But I have lost this single crystal. It goes back to this situation. So I have shear melted the micelles themselves. The whole thing becomes liquid. The moment, because I put a lot of energy into that, the moment I stop, it goes completely back into.
Stop.
Yeah,
Still maintain shear?
no, I stop the shear.
Okay.
So I stop with my rotation. It becomes stationary, and within the time, I mean, I measure. I need at least a few seconds to obtain that. I stop, I measure, I get this powder crystalline.
And this 150 inverse second shear that you have,
Yeah.
you stop that also and take
Yes.
the pattern?
Yes.
The stop means you just seize the
When I see shear, I can see that blurred when I keep shearing. But you have to maintain it very accurately at this. But then it doesn't look so nice. So yeah.
I'm still a little lost. So you shear this for 150 at this shear rate.
Yes.
And then you cease shearing, and the pattern remains stable so that you can take this picture. Is that
Yes,
correct?
for hours.
Hours, I see.
Half a day, days. I mean, I don't have so much time at the synchrotron, but it does. You go away over lunch, you take another shot, exactly the same. Some of these, you can see when you wait long enough that you see this are really a bit larger grains than others. They seem to coarsen and become bigger grains with time. But once I have this, it's very, very stable. And it's like hair gel. When you feel the material in this situation, it's like hair gel. But when you measure then the elastic property, the shear modulus or the elastic modulus of that, the elastic part of the complex shear modulus, is half of this. So the well-ordered crystal is softer than the hard crystal, than the powder crystalline sample. Because there you have lots of grains, and it's harder to shear those grains or to apply. They stiffen up the system. Okay, that's just how we analyze it. I mean, these spectra, what you can do is you azimuthally integrate them, and you get this this picture and my peaks, and this is a BCC, just a way of showing how the BCC crystal looks like. body-centered cubic. Okay. For the last moment, I want to 5 to maybe 6 minutes give you an idea of a very normal system that you all have come across. You have that every day, basically, and that's milk. That's again showing another completely everyday thing, everyday system that obeys Dealvo theory quite nicely, but it's Dealvo combined with steric interactions, and how we modify them unknowingly to get different products. If you take milk, for instance, it contains mainly the proteins alpha, beta, and kappa casein. These two form the heart of of casein micelles, whereas this one is more interesting. It has a hydrophobic part, but also quite a long hydrophilic part with 11 negative charges. The way it looks like is like this. These micelles are about 100 nanometer in diameter. They are important because they accumulate all the calcium in the system, indicated by the orange dots here. But what is important is now you have this micelle with these short charged polymer brush of this overhang of the kappa casein protein. Now, when we think of milk, what you see when you look at, sorry that it's such poor quality, but I couldn't improve that somehow. When you look at milk, this is the interaction potential. Here is 0. Here is the separation between the micelles. That would be the pure van der Waals attraction. This is the Coulomb steric repulsion, and that's the overall repulsion. So milk is stable over a long time. Well, unless it goes off and bugs digest it, and it's not so nice. Now, we have a clearly overall repulsive interaction between the micelles, and that's why milk is actually whitish. Now, when we make yogurt, what happens is you add bacteria, and the bacteria, what they do is they digest lactose, or I'm never quite sure how it goes, but what their effect, their side product, is acidic. So they change the pH, and the pH change makes that this steric brush repulsion goes in, and what you get is what we called a secondary van der Waals minimum. And they get stuck, when you make yogurt, you get stuck in this secondary minimum, and that's why when you take yogurt and you add fluid and you stir it, it dissolves again. You can stir it and you can make it completely homogeneous again, because you can bring them out enough out of this secondary van der Waals minimum. So, but it is a weak gel. Yeah, but it's from the outside. You don't change anything on the casein. The only thing is you change the pH. Take milk and you add lemon juice to it. It curdles because of that. What you do is you change, you screen the charges on the brush, and they shrink. The effective brush width is shrinking, and you feel the van der Waals attraction that is always there, and that lowers this and brings this secondary minimum about. Now, when you make cheese, and that's very clever, what you do is you add something that is called rennin, a little enzyme that basically cleaves off the kappa casein at this point, and that goes in solution, and that stays in the micelle. So what you have done is you just shave off your stabilizing brush, negatively charged brush, you're left over with some hydrophobic core, and that's what you then get. First, it's at the very beginning, not yet fully active. As you start, as you cleave off more and more of that, this interaction comes down until you end up with no repulsive barrier here whatsoever, and just goes. Here, 2/3 of all your micelles are already renated, as they say, and it goes into this deep attractive well. So, by just playing with with the interactions of the same material, you go from milk, yogurt, to cheese. Cheese is irreversibly coagulated. As you know, it's really quite a rigid gel, if you wish. Blue cheese. That's a more tough question, because the blue comes from they soak the they first make the cheese, and then they add breadcrumbs into the cheese that start to, with the right type of mold, penicillin, and that is then starting to mold inside, and that gives you the blue or green color. But it's nothing to do with colloids. So, I thought a long time about that, and you know I'm crazy about food. So this nicely completes the story, because the Romans did know how to make cheese, because the rennin that you need is actually in sheep's gut, and that's what how people discovered it when they pour milk into a water container at that time, which would be a sheep's stomach or whatever, or then they would get cheese. And so they clearly knew about that. Now, before I get to the conclusion, I forgot to put it before. Two more things that not only Romans, but many ancients knew, and that's something that I urge you to do also. It's because it's very simple. The way to make ink is mostly done by carbon black particles, soot particles. You char something, you grind it up, you have small particles, but we know that carbon is very hydrophobic. There's no OH group on that or so. So what they found out is when they coat it with something that is called gum arabic, which is a polyelectrolyte that you get from the sap of only the acacia tree, certain types of acacia trees, then they will coat these particles, and they bring the whole soot particles in suspension. So any ink or pigment-based ink will be based on that. You just use something like a stabilizing surfactant or polymer to bring your pigment particle, which is your colloid, in solution, because you have to somehow deal with it on paper. In the medieval times, people used, for instance, egg yolk, which has lots of lecithin and surfactants in there, surfactant-type material, and they would be stabilizing particles for making egg tempera for paintings, for instance. And also the ancient Egyptians and Romans used something that you wouldn't like to do today, but at that time it was very fashionable to blacken your hair, especially when you get older. Some people suffer from getting white hair. They used at that time galena, which is a lead sulfide colloid, very small, of a few nanometers, and these black dots here, this is a cross-section, electron microscope image of a cross-section of a hair that had been dyed with that. You see these black dots, these are all these colloids that had accumulated in that piece of hair. So you can blacken permanently your hair for a long time with this material. but until you die. You die under yes. Well, you know, beauty has to suffer. So this brings me to conclusion. That means colloids show various phases, for instance, crystals, but many other things. And what is important is they are really different to just simple atoms or molecules in the term that you can tune the interactions. That's something very important. The drawback, again, of colloids is, although they show a much richer, a huge variety of phase diagrams and properties, they are polydispersed, very often polydispersed. It's really hard to get something really monodispersed. A nice monodispersed system is perhaps tobacco mosaic viruses, but you can't do everything with them. And that gives, because of that, this tunability, the interaction potential of the interaction potential, you get this huge variety of systems. And to conclude, also, you're surrounded by colloids. You eat colloids, and that's something that's really quite nice. You can make examples of that, and you see that in everyday life. You play with that, and that's what makes it fun to work with them. Thanks. Let's have tea.
For that very nice introduction.